Good morning, everyone. Welcome to another installment of Engineering 201 Statics. We are in the middle of Chapter 7, and today we'll finish up Unit 3 material in our Blackboard shell. So before we get into the topic, which is shear and bending moment equations and diagrams, we're just going to take a quick step back to talk about beams in general. Is probably something that the textbook should have covered at the beginning of Chapter 7 or maybe even earlier because we've been working with beams. They're just doing a little review of what's going on here with a beam. So a beam is defined as a structural member designed to support loadings applied perpendicular to its axes. Perpendicular to its axes. They are typically horizontal with loadings that are vertical. Also known as long straight bars with cross-sectional area. And what I highlighted here, just mentioned right here, is like if we look at the cross-section, meaning we look at the end of this, it could have this cross-section, which is an I-beam. So there would be the three-dimensional version of it. It could be an H-beam, which is just really that turned on its side. Not very creative, but missing one there. Box beam, obviously this. L beam is really just an L bar. You may see that in shelving and things like that. And there might be some other options for us, but that's really just talking about the cross-sectional area. We don't worry about that so much. That is part of the design of the beam. Once we know the loading, on the beam, the extreme loading, the internal and the shear force and the bending moment, then we can go and design and choose what cross-sectional shape we'll use for that beam and that design. So, all right, so types of beams. Beams can be classified according to the manner in which they are supported. The manner in which they are supported. We've been dealing with these two. Cantilever, which is fixed at one end. Cantilever will have Y and a moment. So it'll have a support reaction, the X and Y, in a moment, and it's free at the other end. Simply supported just has the reactions at the end. It possibly could have a moment, but usually that's a pin connection there at that end, so there's no moment there. So cantilevered and simply supported are probably the two most popular. These remaining ones are more a combination of those. Here's an overhanging, which is really just simply supported. Here's continuous. That's also simply supported. Cantilever with, this is sort of a combination right there of the two. And then this last one, fixed end or fixed ends, both ends fixed. This is actually what we refer to as statically indeterminate. Okay. Indeterminate. Basically fancy word to say we can't solve it using our traditional ways of solving static problems like some forces, some moments. We have to look at some other ends. And why is that? Well, with a fixed end, we're going to have support reaction there. We're also going to have support reaction there. And there, right off the bat, we have 6 unknowns, but we really only have 3 equations to solve that. So we run into a little trouble. We have to use some other equations to solve anything like that. All right, so that's a type of beams there. And again, to design a beam, we need to know, and this is a little bit of review because the book did cup on that, or mentioned this earlier. Need to know the internal shear, which is V. and we need to know the bending moment, which is M. And then we add those together with the design code. And we can design beam that's will work for that situation. So design code, theory of mechanics and materials, which is a follow-on class of this if you end up taking that. All right, so moving into this idea of the shear and bending moment equations and diagrams. Up till this point, we are finding the shear and the moment at a point. And the way we did that, let me just pull up a diagram here. I'll copy that over. We were finding shear and bending moment at a point. Let's say we were finding it at point C. And what we did is we did a free body to find the support reactions. And then we did a cut at the point, which is really just using method of sections. And then we applied our equilibrium equations, which hopefully you know by now is some force is 0, some moments equals 0, and basically solve. So we're using the support reactions, finding support reactions, and then we would cut it at the point of interest, and then we would section it. And the idea was that we would be able to solve. And that's what we did last week in lecture and also in an earlier section in the textbook. Now, we would only find the shear and moment at a point that we chose. Now, the whole purpose of finding out these loadings internally is so we can design the beam. But to design the beam, we need to know what the maximum and minimum are. Or the maximum, but we want to know the minimum because it shows us some other things. Find the maximum internal shear and bending moment, and then we can use that as a design limit in the beams. You know, we don't want to design a beam to support 100 pounds if it's going to experience a loading greater than that, because that's where we set ourselves up for deformation and potentially failure. So we want to find what the maximum we expect is, and then during design, they'll actually add a factor of safety on top of that, just to be extra sure. It's kind of like a elevator. They can design it to hold 10 people, but because they figure that's the max number of people going to be in there, but they know that people aren't counting as they get in the elevator, so they're going to design it for a few more than 10, knowing that it possibly could go that high. So to find out where the maximum is, we'd have to pick almost an infinite number of points. Now we can make some guesses as to where that's happening. Maybe it is happening at B, or maybe it's happening in the middle here, or maybe it's happening at A. But we'd have to check all those points. So the idea is if we could look at this structure, this beam here, and if we were able to generate equations that would tell us the shear as a function of x along that beam, or the moment as a function of x, you know, x being from the left end along the beam, we could see from those plots what is happening. So what we're going to end up doing here and learning about this is we're going to take this structure and we are, wherever there's a loading on it, an external load, we're going to draw these lines down. And then we're going to draw some horizontal lines. And what we're setting up here is finding the shear and the moment as a function of x along that beam. So just faking it here, we might find out that the shear goes like this. If that's 0 and that's 0, it starts up here, goes down here, and then comes here and does something like that. Then it's very easy for us to find out where the maximum shear occur. And then if we look at the bending moment, the same thing. And again, I'm just making something up here. I'm not saying this is exactly what's happening, but the idea is we can then find out where the maximum occur and find out what those values are instead of having to look at every possible point on there. So we're really just trying to see how the shear varies and the bending moment varies across the beam. And our process is going to be very similar to what we did over here when we found shear and bending at a point. We're going to shear so we're going to find the shear and bending moment along the axis as a function of x. So our process is very similar. We're going to free body diagram all to find, again, the support reactions. Nothing new. We're going to draw and set up the plots. That's really drawing this part right here. And we're going to do it directly below that problem of interest, just so we can see it in relation to or right below where support reactions are, where point loads are, where bending moments applied are. And we're going to start seeing some things happen commonly across different problems. So free body, find the support reactions, draw, set up the plots. And here's where we're going to be different. We're going to section between changes in loading. Between the changes in loading. Okay. Now, what does that mean? Well, here we have loading here because there's a support reaction. There's loading here, support reaction. There's some loading happening at the end. So those are external loading. We also have this distributed loading. But basically, we're looking between the changes of this one, and this one. So we're going to end up with 3 loadings here. We're going to set up 3 sections. We'll have a section that goes from here to here. We'll have a section that goes here to here. So we're actually setting up 2 sections and the 3rd section at the end here. Right? So we're sectioning between the loadings. So we'll create, in this example, we'll have 2 sections, and then we just go and continue what we did before. Some forces, some moments about the cut, and we just solve and plot. So very similar, still using method of sections, but instead of sectioning at a specific point, these are going to be sectioned at our coordinate or distance of x. Because we're measuring everything from over here, x equals 0. It'll be a distance x, which means it applies to everything between here and here. So one section in this example is going to go from, if I can read that, That's going to be between 0 and 8. And the section will be between 8 and 11, which is the end. So that's 0, there's 8, there's 11. We'll section between those, and then we can find out how it varies. So it's really between the loadings. We could say it's between where between any discontinuities, changes in the loading. So it starts over here, it changes here, and then it goes on a little further, and then it changes again here, and then it changes again here. So really end up having 2 sections that we're going to work with. Now, why are we only doing shear and bending moment? What about the normal? Where'd the normal go that we were dealing with last time? Well, again, beams are meant or designed to support vertical loading. Not so much concern about things perpendicular. So we normally don't consider that in analysis. And with the load being applied vertically, the horizontal axial load really doesn't come into play. All right. Say another way, beam's resistance to shear and bending is more important in the design of the beam than its resistance to axial loading. That's really what we're looking at. All right, so continuing on with this, we're going to use the same sign convention. Let me just do that again. When we shear that beam, we're going to have the same design convention, meaning what's plus, minus, and all that. Our shear is always going to be down on this side, up on that side. Again, we're looking for a clockwise rotation. The moment, again, is setting up to create a smile. So if we have the moment on this left Twix, it's that way. If it's on the right Twix, it's that way. Okay. And we set up the moment that way. The idea is it's setting up compression on the top and potentially tension along the bottom. And shear, again, is clockwise rotation. All right, so again, our process, our procedure, support reactions after getting a free body. We won't always need them on both ends. So in my practice, I tend to find the support reactions that are going on the left end, and then we figure out the right end as needed. Sometimes we won't need them, other times we will. And then we just continue with our process. So I'm going to go through here and just go through a simple example explaining how to solve this. We have a beam here. We're going to have force of tension up. And let's say that's 600 pounds. And this object is hanging and holding up some big structure here, an engine or box or crate. So when it's put right in the middle, so we'll make this 1.5 meters and this is 1.5 meters, so it is in the middle, that we would put half out at this end, half and half, which means we're going to have 300 pounds here and 300 pounds on that end. So that's going to be our beam. While we're here, let's put together the, so I really have already done the free body diagram is what I'm saying here, just by inspection. But if we had done the process, We had done the free body. We don't have anything axial. We don't have any moments happening at the end because these are just hanging, right? Just hanging chains. So I did the free body and we found the support reactions. Check. Now we'll set it up. And again, this may be already done for you when you take a paper exam. On the computer, you would have to set this up yourself. So let's draw some lines here. We're going to have one here. And we'll have one in the middle. And we're going to have one here at the end. Now again, why is there only 3? Well, we're looking where the loading changes. So it starts here. Then it doesn't change until it gets here. And then it doesn't change again until it gets here because there's no other external loadings on that. Let's put across our shear. I guess that really should end when it gets there. And there's our bending moment. So we've really just set this up. Come on. And then we put units here. This is obviously going to be pounds, and this one would be foot-pounds. So that would be technically what we have to set up. Now, just looking ahead, when we have these vertical lines here, 1, 2, 3, what we're expecting is that the diagrams are going to change at that point. There'll be some sort of change in the slope or the value or the magnitude there. All right, so moving on. How many sections do we have here? Well, here's a change in loading. Here's a change in loading. There's a change. So we're going to have section 1 and section 2. Let's put these over to the right here. Section 1 is going to be where I take X to go this far. So it's going to be between 0 to 1.5. That's my first section, right? I'm looking at this area to this area. We're going to see what happens between those two loading changes. So if I cut that and I make a little section here, this distance is going to be X. I have a loading down here of 300. I'm not at the 600 loading in the middle yet. So I will have shear there. There's my moment up. Okay. Now our distance now is a function of X. So when we do the moment, we're going to have an X in there. So looking at this, we're going to sum forces in the Y direction. Positive up. We're not worrying about the X direction again, remember, because we're not doing axial load. And on this, we're going to have minus 300. Minus shear equals 0. Therefore, shear equals minus 300. So what do I do with that? Well, that shear now goes over to this diagram, and we're going to find minus 300. And since it equals minus 300 for this entire range of 0 to 15, it's going to go across there at minus 300. Meaning there's no change in shear from 0 to 1.5. All right, that's section 1 again. Let's look happening at the moment. So counterclockwise, sum the moments about the cut. That's very important. That will be 300 times X plus M equals 0. Solve that. M equals minus 300X. So through that section, it is following that function. That's a linear function. We have to evaluate that at both ends. So I'm going to evaluate it at 0 and 1.5. So the moment at 0 is going to equal 0. Pretty easy. The moment at 1.5 is going to equal 3,450. And it is a minus, so it's going to go down here to minus 150. There's how my bending moment is changing. That would be right there. M equals minus 300x is the function. It's linear. And it goes down to a minus 450. All right, before I continue, let me ask in the chat, any questions on how I found that? Personally, I think that's pretty cool. All right, so how do we do the second section? Well, there's two ways to look at the second section. Section 2 will go from 1.5 to 3. I mean, it really goes from all the way from 0 to 3. We're not just taking section 2 by itself. So I should make that, actually it goes from 0 all the way to 3. I'm going to redo that. When I said 1.5 to 3, I was meaning that it is looking at what's happening between 1.5 and 3, but we still have to make that section the entire length. So when I make that section, it's going to go all the way over. I'm going to have the 300 down, the 600 up because I've passed that, but my distance here is x. And on the end, again, I have the shear, and there's the moment. I'm now over in this section, right? So I include this, the 300 on the left end and the 600 on the other. Now, let's say this was a really long problem. Okay, really long problem, and I had to do like 3, 4, 5 sections before I got to the last piece, which is the very end. You can take it from the left end because that's where x equals 0. You could also take this from the right end. From the right end. And let me draw that in the middle here. That would be drawing a section that starts from this end. There would be the 300. We would put the shear up, the bending moment up. But here's what's important. When we do the x value, x is from here to here. So this distance from here to here is really 3 minus x. And that's the little thing you have to be very careful if you choose to use that right section. Okay? I'm going to solve it right now using just the left section, meaning measured from x equals 0 from the left all the way over to that second section. And then I'll show you real quickly how we get that if we use the right section, because that's another way to do that. All right, so we have the cut here. Let's come down. We're going to sum forces the y direction equal to 0, positive up as always. We're going to have minus 300 plus 600 minus v equals 0. That means v is going to equal 300. I bring that over here. That means that's plus 300. And it doesn't change for that entire section. There's the shear for the right section. Now to check this, at the ends, we want this to come back to 0. And since this 300 right up here is a minus 300, it's pushing down, it takes it from 300 down to 0, so that makes sense. Same on this side. This is pushing down 300, so it goes from 0 down 300. So that makes sense for me. It works. Looking at that, we can see that the maximum shear occurs right here. Why do I say it occurs right there? because right there, there's a difference of 600 pounds, a change of 600 pounds. It goes from negative to positive. So if we're concerned about this shearing off, that's where we'd expect it to possibly happen first, assuming the beam was continuous in materials and setup and it was the same all the way across. We would be concerned about that. So we use 600 as the maximum shear. All right, moving on, and we go to the bending moments. The moments about the cut, again, that's important. Counterclockwise positive on this section. It's about the cut. We're going to have 300x minus 600. What is that going to be? 300x minus 600 times. Now, again, we're using this distance from the 600 to the cut. What is that distance? That distance will be x minus 1.5. From there to there. X minus 1.5. And then here at the end, we just plus m equals 0. I'm going to bring this all the way over here now. Therefore, m should equal, if I go through that mess, 300x minus 900. And that's our moment across that second section. Now we have to evaluate it. So I'm going to evaluate it from 1.5 to 3.0. Moment of 1.5 gives us minus 450. That's that point. That's good. And the moment at 3 is going to be 0. So I connect those two. I can put more points in there. That's a linear function. I can connect those two. And it brings us back to 0, which corresponds to what's happening at the ends because there's 0 moment there. Therefore, I'm happy with that solution. So looking at that, if we were looking to go design or tell our designers what to use, we'd have a max shear of 600 and a max bending moment at 450. And they would occur right in the center, so they would need to know to design it thicker there or bigger, more robust at those points. All right, question on that problem. On the exam, if you get a question like this, you'll be given the problem, asked what to find, find a shear and bending moment, and you're going to have to give the solution for it. I need to show all the work. You just can't sort of guess what's going on there. I need to see where you got all these points. I need you to label any points where it changes. So I would need to know what's happening here, 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 and here, and then the bending moment here, here, and here, and then you draw the lines and shade in between. All right, questions on that one? All right, let me just show you down here. If I choose to take the section from the right end, and that would be, I cut it like this. I have 300 down, X is to here. Again, shear moment. And this distance, here's the important part. This distance right here is going to be 3 minus X. And that's what we use if we solve it from that end. So let's go through and do that just as a check. I sum forces in the y direction equal to 0, positive up. I'm going to get shear minus 300 equals 0. Therefore, shear equals 300. That corresponds to this. So that's cool. And we sum moments about the cut equal to 0. We're going to get minus shear times 3 minus x minus m equals 0. I'll get the moment function to be 300x minus 900, which is exactly the same as we got right here. So that checks. So that's a way of looking at from the right end. Sometimes it's a little easier. Not always, but something to consider as we do these. All right, want to do another problem here. This one's a little messier. And it's messier in that includes a distributed load. So let me go to this one. And let's begin by setting it up like we normally do. Again, I'm putting it where I had the changes in loading, or the loading is discontinuous, I guess is the appropriate way to say it. And that happens at these 3 locations. And let's go shear across. And here will be our bending moment. And shear is going to be in kilonewtons. Moment's going to be kilonewton meters. And we want to draw the shear and bend diagrams for the beam. That's what we're told to do. All right, first thing is free body diagram. Define the supports. Let me just draw that real quick. I'm actually going to copy that over here so I can draw directly on it and see if we can do this. And I'm going to stretch it out just so it's a little cleaner. All right. So a pin there, we're going to have a Y, a roller at B, so we're going to have a BY. We have this distributed load right here. So when we do the free body, we're going to look at that as a sum of the resultant force there, which is going to be 40 times the span of 8, which means 320. And that'll be acting halfway. Make it a little taller so I can read those numbers there. All right, free body diagram. If we go through that, find the reactions, free body the entire thing. I would start out by summing the moments. About the end, probably. Yeah, about the end. Counterclockwise there. We're going to go through there. We have minus AY times, what do we have here? AY times, is it 5? Oh, I have some different values there. Sorry. That's going to be, let's see. Now I'm going to do about A. Let's change that up. As I look about this, I can go about C. It doesn't really drop anything out for me. I want to drop out one of these. I want to drop out one of these loadings, either this support or that support. So let's do about A. And we'll have CY times hang on a second. Why do I keep saying CY? I don't have a CY. All right. Let's start this again. Had a little brain freeze. I've been off Mountain Dew for the past 2 days. So maybe I'm just going through a little bit of withdrawal here. All right, just give me a second. All right, sorry about that. I had to gather my thoughts and had a quick interruption here. So Matthew's question: do we combine moment and Y force at C? Those are, one is a vertical loading and one is a moment, so we have to keep those separate. What I want to do though is, in finding these support reactions, I want to find out what's happening at A and at B. A and at B. So let's start out by summing moments at A. That should get rid of what's happening from the AY. And there's BY. And we will have, again, that's 40 times 8, that's 320. So the moment about A, that should be a minus 320 times half of that, which is 4. That's going to be a plus BY at 8, a minus 150. That's how we include that one. And that'll be a minus at the end here, 20 times 11. That should equal 0. And if I go through that mess of BY, I think it comes out to be about 206. And then I can sum forces Y direction equal to 0, positive up. And I should come out that AY's 134. And that's going to be from AY minus 320 plus BY minus 20 equals 0. So 134. So 134-ish, and right here we have 206, and then nothing happening at the end. All right, so that's just doing the free body. That gives us a point there. Now understand, when we have that 134 at the end, we're sort of expecting that the 134 will jump right here too. Jump up by 134. So that's sort of our expectation for that. So sections, what sections are we looking at here? Well, we have a discontinuation of loading there. We have one there. and we have one there. So we really only have two sections. One section will go from X into this, and the other one will go from X into this. Okay. All right, so let's do the section between 0 to 8, right? Hello. 0 to 8. If I draw that section real quickly, I get this. I have 134 up. I have the shear there. I have the moment there. How do I deal with this loading up on top here? Well, I'm still going to have that loading as far over as the cut. It will be X long. So the resultant force that I use, which is right here, right? We did one originally up here. That is going to equal the 40 times, so we're basically getting the area of that rectangle, the 40 times distance X. So that's going to be a 40X force acting at X over 2, right? Because it acts or is applied halfway across. So when I go to sum forces for the shear, let's do that. In the Y direction, positive up, I'm going to have 134 minus the shear minus that 40X. Equals 0. That tells me that the shear is going to equal, I'll put it as X, is going to equal 134 minus 40X. That is the function for 0 to 8 for the shear. So if I go and evaluate that at 0 and at 8, at 0, it's going to be 134. So right there it is, 134. And at 8, it's going to be 134 minus 320 equals minus 186. So this is going to come down to minus 186. It's going to cross there. And there's the shear for that section. Now, how do we find that point where it's going to cross over right there? It's not necessarily in the middle. What we do is take this function and we set the shear equal to 0. If we set the shear equal to 0, that becomes 134 divided by 40. That's 3.35 is the X value. And then if we evaluate that, we should get 0, and that corresponds to that point. So on an exam, I would want to see all those points, the 134, the 186, and then the point in the middle where it crosses 0. And that's where the shear crosses 0. Okay, what about the moment? Sum the moment about the cut equal to 0. Counterclockwise. What do we have here? We have the moment minus 134 times X, right? Here's the distance X from the cut. Plus, that's the resultant force, which is 40X times the distance, which will be X over 2. Right? Here's the resultant force. Its distance is half, so it's X over 2 right there. All that mesh should equal 0, so our moment function at that point is going to equal 134X minus 20x squared. So we have a function to the second power. That means it won't be linear. It's going to be parabola. And we need to evaluate that at 0 and 8. At 0, it's going to equal 0. Nice. At 8, if we evaluate that at 8, so that's 20 times 64. Let's see, 134 times 8 minus 20 times 64 minus 208. And that's a parabola. We would have to find some others. We can find the maximum or where it crosses. We can set this equal to 0. I mean, we can set the moment equal to 0. Sorry, let me change it up. We already did set the moment equal to 0. Or where it's going to equal 0, and we can say that again. We set that equal to 0, right? Equals 134x minus 20x squared. We'll get x equals 0 as a root, and x equals 134 divided by 20, 6.7. So at a distance of 6.7 over, this is going to cross the 0 mark. If we take the derivative and set it equal to 0, we can find the maximum, and we'll find out that it's going to do this. And this max point up here will be about 224. Sort of doing that in my head. Right, derivative of that is going to be 134 minus 40x. And we put in 6.67. 40 times 6.7 minus 134. All right, so what's happening in the left side? This is a little busier one, I get it. We now want to look at the section 2. That is going to be from 0 to 11. And again, this is a section where we could either use, sorry, that's a little longer than that. We could either use this extended left section, or we could use the right section, which has a lot less going on. And I'm going to choose to use this right section just because it'll be cleaner. So let me draw that. We're going to have 20 down, 150 this way. Shear is up, bending moment's up. Now again, this distance here is the x to the cut. This distance here is going to be 11 minus x. And if we can avoid using that distributed loading across that, that certainly makes it easier. Some forces in the y, that's going to be the shear. Plus v minus 20 equals 0. So that becomes a shear of 20 all the way across. And that shows that the biggest jump in shear is actually going to be right here of 206. That's a change of 206 right there. All right, we sum the moments about to cut equal to 0. We're going to have minus m minus 150. Don't forget that on the end. And then we'll have the plus 20 times 11 minus x equals 0. We should get a moment function there that's going to equal 20x minus 370. We evaluate that at 8 and 11. At 8, we should still get the 8, that's 160. We should still get minus 210. Try it again, minus 210, which corresponds to this. And at 11, we should get 11 to 20, 150. So there's minus 150. And that is a linear function, so it's going to be a straight line from there to there. And that sets up our completed bending moment diagram. Now, before we go any further, let's do a quick check on any of those answers just to see. On the left end, we have a shear up of 134. That should correspond to that. It does. Here we have a shear up of 206, so we should see a jump of 206. We do. Here we have a down 20 shear, so we should see a down 20 to get back to 0. We see it there. And as far as the moments, at this end, there's 0 moments, so that should correspond to that coordinate. And at the right end, there's a moment of 150. That should correspond to that, which it does. I feel fairly confident about the drawing that we came up with there. All right, questions on that problem? That's a much more complicated versus the first one, but the same process. Okay, I'll take that as we're good to go. There's a little bit more we need to complete for this chapter to finish up chapter 7 for this unit 3. It's dealing with cables. There is a section there. It talks, I think it's 7 point, the end of 7.3 maybe, where it talks about some shortcuts in doing these diagrams. And we've already talked about those, in that when we see a shear up of 134, it should jump up by 134 here. It jumped up by 206. It should jump down by 20. Those are the shortcuts. Just look through those briefly. The last part is dealing with cables as a structure, like holding up stoplights or signs, things like that. And I'm just going to ask your patience on this. I'm going to need to take a break and get some throat lozenges or something going on here. And so what I'm going to do is close out this section for the lecture. And then a little later this morning, I'm just going to record the cables one. It's fairly short, so I'll put that in its own little lecture recording. And it should be a short one. It should be posted hopefully here before lunch. So I'll just appreciate your understanding on that, just leaving it as is. So as I always do, I will end here and ask if there's any questions. And otherwise, we are done for today until I post that one on cables to finish up chapter 7 here. Hopefully, excuse me, hopefully sooner than later. So any questions before we close this one out? Reminder that we have exam 3 next week, next Wednesday night. All right, thanks, Matthew. Have a great day. Everyone else, I'll stop the recording now. If you need to hang on, ask questions, or you can let me know.